Okay, welcome to chapter 19. This is plate tectonics. This is a beefy chapter. There's a lot of information, but it's also basically bringing together a lot of what we've learned so far and creating a kind of a cohesive framework for basically how Earth Earth's interior interacts with Earth's surface and the atmosphere, and basically how Earth as an engine works and how Earth loses heat over time. So, plate tectonics is we call it the unifying theory because it's able to explain a lot of different data sets from rocks, from landscape features, from different structures that we see, why we see faulting, where we see faulting, earthquakes, volcanoes, all that stuff. So it brings together everything and creates basically this unifying picture of how everything relates together. So let's go ahead and get started. So plate tectonics is the general idea that Earth's surface is composed of large, thick plates that move slowly and change in size. So they move relative to each other. And where we define a plate boundary is where plates are either moving away from each other, toward each other, or past each other. And this creates intense geologic activity. So here, this picture is showing some of the kind of the larger plates that we have. There are several, so this is a more generalized picture. Over here in Western Pacific, in the Indonesia area over here, this gets really complex. The plates are broken into what we call microplates and all kinds of stuff like that, really complex kinds of boundaries. But this is the general picture of how Earth's surface is broken into different plates. So here we've got the African plate, we have the Arabian plate, the Eurasian plate, the Indo-Australian plate, we have the Antarctic plate, we have the Philippine plate, the Pacific plate, the North American plate, the Cocos plate. Up here, we have a little bit of this Juan de Fuca plate, which is really important for us, which we'll talk more about. The Caribbean plate right here, the Nazca plate, the South American plate, and the Scotia plate here. So anywhere, depending on, what map you're looking at, anywhere from like 13 to 16 major plates that Earth's surface is broken into. And again, these plates are defined, their boundaries are defined by the relative motion of the crust, basically on either side of that boundary. So if we see that the crust is kind of moving away from each other, then we define that as a boundary. Or if we have two pieces of crust that are converging, then that is a boundary. Or if we have two pieces of crust that are sliding past each other, then that is a boundary. So we'll talk more about what these different boundaries are. But the main three types here are divergent. This is where plates are moving away from each other. And so that's defined by this symbol right here. So we can see throughout the oceans, those are largely divergent boundaries in the middle of the oceans here. So that's essentially the mid-ocean ridges. We have convergent boundaries, which are these bold lines with these triangles or these teeth pointing towards the overriding plate. Basically, it's where two plates are coming together, and you can see a lot of those happen along the edges of continents here, largely between oceanic and continental crust. But there are some areas like over here between the Philippine and the Pacific plate where we have ocean-ocean convergent boundary. And then over here, the Himalayas between India and Eurasia here is a continent-continent convergence. So we have different types of convergent plate boundaries. I'll talk more about that. And then transform here. So transform boundaries, recall those connect ridge segments. So all these lines that you see between these ridge segments right here, those are transform plate boundaries. So that's where we have crusts sliding past each other, and it generates those fracture zones that we saw in the previous chapter. So the theory of plate tectonics developed from two different hypotheses, two different ideas. The first one is continental drift, and the second is seafloor spreading. So we're going to first talk about the early stages of continental drift and why that was initially shot down for several decades. So continental drift was first proposed by Alfred Wegener in the early 1900s, and he noted that there's almost a puzzle piece fit of the coastlines between Africa and South America. And that's also been known for a really long time. So basically, if you look at South America here and Africa, if you were, especially right here, if you were to just kind of squeeze them together across the Atlantic, it looks like they would actually fit together fairly well. So that's been known for a really long time. But Alfred Wegener, took this a step further, where he actually noted that South America, Africa, India, Antarctica, and Australia have almost identical late Paleozoic rocks and fossils. So the Paleozoic started in the Cambrian era, which was about 542 million years ago. And it ended about 252 million years ago with the greatest mass extinction event in Earth history, which is the Permian Triassic, the PT boundary. So late Paleozoic, we're talking like 270 to 250 million years ago. So here we've got different types of fossils that he noticed. So we've got Glossopteris, which is a plant, it's a tree fern. And we actually see Glossopteris. So if we look at this as a kind of a fossil map over here that shows what these different continents or what these different um, basically land masses would have looked like if they were together. So we look at Glossopteris here. So it's this tree fern right here. We can see that we actually find fossils of Glossopteris across South America, Africa, India, Antarctica, and Australia. So it's across all five of those continents, of those land masses. We also noticed that there's Lystrosaurus and Cynonathus. So these two guys right here, you can see they're kind of reptilian-esque. Um, so Cynonathus, we found fossils across South America and Africa right here. And Lystrosaurus found in Africa, India, and Antarctica here. And then we've got Mesosaurus. So these are freshwater reptiles. So right here, Mesosaurus. Freshwater reptiles. These fossils are found in Brazil and South Africa only. And so freshwater reptiles do not generally like to swim in saltwater. They don't like oceans. Their bodies cannot handle that change in water chemistry. And so the fact that we see Mesosaurus across these two continents here, they're fossils across these two continents, um, which are currently separated by thousands of miles of ocean. It's really strange to find both of these across, or both fossils across both of these continents for a freshwater reptile. And if we look at Cynonathus here and Lystrosaurus, these guys have short little stubby legs, which are not meant for swimming. So for them to be found across, if we take our current positions and say the continents have not moved, it's really strange to find all of these fossils here, basically that have traveled across many thousands of miles of ocean. And Glossopteris, which is a tree fern, typically, and what we now know after studying it is that it does not disperse. It seeds and its pollen through wind. So it's basically a land dispersal. But we didn't know that back in the day. But he looked at these fossils in particular, and additionally, the sequence of rocks that we find, especially across South America and Africa. We say the same sequence of rocks across these continents and the same fossils within that sequence. So if we use the law of lateral continuity, that tells us that these would have formed in the same place because if they are currently separated by, 3,000 miles of ocean, it's highly, highly unlikely that we would end up with the same sequence of rocks, the same sequence of fossils, the same structures within the rocks, in two completely different locations. So it makes much more sense for these continents to have once been together to create all of these different fossil assemblages and distributions and the same sequence of rocks across these land masses. So up here, this is just showing an idea, the early idea of continental drift. So, about 225 million years ago, you had Pangaea, which had been around for a little bit of time. And then over time, that began to break up here. So the northern part, which is called Laurasia, and the southern part called Gondwana, would have begun to separate. This is 135 million years ago. And we have basically the opening of the kind of the proto-Atlantic. This would have started about 200 million years ago. And then as these kind of new plate boundaries would have formed, it would have pulled these continents apart. Here, this is what the continents would have looked like about 65 million years ago. So this is when we had the death of the dinosaurs. The Atlantic was still opening. The northern Atlantic in particular hadn't actually been opened yet, but the southern Atlantic here, and the mid-Atlantic, was continuing to open. And then over time, we have the ocean getting bigger, the continents getting farther apart, and we have basically a separation of these land masses over time. So we'll talk more about how we can do that. So here, Pangaea. So you've probably heard of the term Pangaea before. This was the supercontinent that was proposed by Alfred Wegener. And it's made up of two parts. So Laurasia is the northern part of the supercontinent, and that contains North America and Asia. This excludes India. At the time, India was not in the northern hemisphere. India was actually in the southern hemisphere. So the southern hemisphere, the southern portion of Pangaea is called Gondwana or Gondwanaland. This is the southern supercontinent, and that would have contained South America, Africa, India, Antarctica, and Australia. Basically, those 5 land masses that contain the rocks and fossils that we talked about in the previous slide. So not only do we have evidence from the fit of the continents, from fossils found across all of the southern land masses in particular, and then also the sequence of rocks found across these different land masses. We also have basically different climate features. So in particular, in the late Paleozoic, so again, late Paleozoic, that's like 270 to 250 million years ago, we have glaciation patterns that are evident on the southern continents in particular. So if we look here at the southern continents down here, these parts that are closer to the pole, so we call these high latitudes because the numbers are higher. Low latitudes means you're closer to the equator. You're looking at lower latitude numbers. So high latitudes, you're closer to the poles. We see different glaciation patterns. And so here, this is if we take the current position of the continents, this is what these glaciation patterns would look like present day. So we can see that for South America here, glaciation patterns looks like the ice actually flows from water onto land based on the way that it looks like basically how the glaciers moved over the surface. So glaciers kind of pick up stuff underneath them as they move across the land. And in so doing, it creates kind of like a sandpaper or like a grit that kind of scratches at the rocks as the ice travels over it. And so it creates these glaciation lines in the rocks. And so we can look at the direction, we can use those to figure out what direction the ice was moving in. And so if we take our present day continent locations, we can see that for South America, it looks like the ice was actually flowing from ocean onto land. For Africa, it looks like we have kind of this central point down here, and then the ice was flowing off in all directions. For India and Australia, the same thing with South America. It looks like ice would be flowing from ocean onto land. We know that that does not happen. We can look at modern day glaciers, where they form, and modern day ice sheets and where they form and how they move. Ice sheets and glaciers form on land and move downhill due to gravity towards sea level and the ocean. So if we keep our continents at present day locations, these movements that we see here, especially for South America, India, and Australia, these movements do not make sense. Ice does not form on water and move onto land. Ice forms on land and moves onto water. So if we take all of these Gondwana continents here, these Gondwana land masses, and move them basically back to the positions that the fossils and the rocks say they should be in, and the fits of the continents as well. And if we look at the glaciation patterns, this makes a lot more sense. So basically, we had ice forming on Antarctica and on parts of Africa and moving outwards from there onto these other land masses. So these glaciation patterns make more sense if we have these southern land masses here all together instead of in their present day locations through time. We also have coal beds that were deposited in the northern continents from swampy, probably warm environments. So coal beds, coal tends to form in swampy, boggy environments where you have a lot of standing water. You don't have a lot of movement in the water, so there's not a lot of oxygen in the water for microbes to break down that organic material. So all those plants are able to get compressed and turn into coal. So we see coal bed at the same time in the late Paleozoic, we see coal beds in the northern continents here in North America and Eurasia. And that makes more sense if these are in our lower latitudes, in kind of those more warmer environments where you're able to have more standing water and create more of a swampy environment. So looking at basically these different climate patterns, so the way that coal forms and where we see coal beds and the age of those coal beds, and then these glaciation patterns gives really big clues for basically the location, the latitudinal location of Pangaea. So we can use these kind of like paleoclimate belts. So basically looking at different rocks from this time period that would have formed during this time period, and different structures, like, cross stratification and preserved ripple marks and those other kinds of sedimentary structures, to figure out what kind of climate those rocks would have formed in. So this is the power of sedimentary rocks. They give direct evidence for what environment they formed in, and then we can relate that to essentially the climate. So we can use rocks from this time period, from the late Paleozoic, to kind of reconstruct what these paleo climates, so paleo is past, so what these past climates would have looked like. So here we have basically at the poles, I'll explain what this is in a minute. At the poles, we see more glacial environments. And then as we get kind of our mid latitudes is more deserts. And then as we get towards the equator, it's more tropical where we see more reefs, more limestones, stuff like that. So our low latitudes are equatorial, and our some of our mid latitudes, we tend to see like more coal beds and stuff like that, and more reef type environments, more tropical. So using these paleoclimate belts, we can look at essentially how those would have been generated and why they differ from our present day location. So we have what's called polar wandering as an idea to explain these climate belts and kind of the offset from our present day climate belts. So polar wandering is the apparent movement of the poles. So here, this is showing an apparent polar wander. So if the ancient pole right here, so based on paleoclimate belts, so where we see rocks from a certain time period showing where we see more ice, where we see more deserts, and where we see reefs here, we can say that, okay, so our ancient poles must have been at this location here in order for there to be ice. And then our equator would have been basically halfway in between them, and that makes sense for where we see reefs, because reefs tend to form in tropical areas. But our present day pole right here, you can see the continents in the background. This is our present day pole, which doesn't match where these paleoclimate belts are. So one way to explain this difference, this mismatch, because for our present polar location, we would have ice up here, ice down here, we would have deserts in our mid-latitudes, and then our tropics right here would be our reef. So there's a mismatch between basically our paleoclimate belts and our current climate belts. So one way to explain that is with polar wandering, which is the apparent movement of the poles. So basically the poles would have shifted over time to account for this change that we see, this mismatch in our climate belts over time. There's another way to explain that over here. So this is kind of scenario A, where the paleoclimate belts can shift because our pole is shifting. But scenario B over here is, well, actually, there may not be any paleo or any polar wandering. Instead, it's the continents that are moving around that are creating these paleoclimate belts that we see. So in scenario B over here, the ancient pole position and the present pole position are the same, and the continents here are what are moving around to create this mismatch in the paleoclimate belts. So these paleoclimate belts, again, the evidence for this can be explained in actually three different ways. So these are kind of our end scenarios right here. So the continents remain motionless, which is scenario A right here, and the poles actually moved, which is polar wandering. We have scenario B over here, which is the poles did not move and the continents moved, and this is the hypothesis of continental drift. Or you can have some combination of scenario A and scenario B, where you have some polar wandering and some continent movement to account for these changes in paleoclimate belts from present day. And so if we look at the apparent polar wander of the South Pole since the Cretaceous, so if we say the continents have not moved around, it's the poles that are moving around, we can see that since the Cretaceous, which is the Cretaceous ended 65 million years ago. So this is through the Cretaceous. The South Pole was right here. In the Eocene, it moved up over here. And then in the Miocene, we can see it moved quite a bit over here. And then the beginning of the Quaternary, it moved down here. And then our present day pole location is right here. So this is actually some pretty significant movement, and it would change the climates of the surface because it's changing the amount of solar radiation that's hitting the surface over time. But this is pretty significant movement. And we actually do have evidence. So I don't know, when was it? Was it back in like 2018 or something like that? We actually do have evidence that our pole does shift around a little bit. And that's why any kind of military or people who use compasses a lot, magnetic compasses, have to constantly adjust the magnetic maps and their magnetic declination because the magnetic pole does actually move around in our, so this would be, yeah, that would be our magnetic pole. Or that would be from our using our paleoclimate belts, which is kind of matches more or less the geographic pole. But we do see that it actually does shift a little bit over time. But that came much, much later with new technology. So the early case for continental drift, and there's a lot of different evidence to support this hypothesis. So again, you've got the fit of the continents, you've got various rocks and fossils that seem to match across Gondwana in particular. We have glaciation patterns, we have coal bed locations, we have paleoclimate belts, lots of different things that could suggest that the continents have moved over time. They've drifted over time. So it's a very big idea to kind of try to wrap your head around. And so it was met initially with a lot of skepticism because people came up with ideas that could explain all of these different data sets without the need for continents moving around. So people could explain why we see fossils across different continents as, maybe there were land bridges that these creatures could have walked over at the time. Wind and ocean currents could have distributed Glossopteris Glossopteris pollen across those different continents. Polar wandering could explain why we see fossils. So basically, um, continents moving around, why we see different fossils in different locations. And the paleoclimates at the time could be from polar wander. It doesn't necessarily have to be from continental drift. So that it was met with a lot of skepticism and potential other explanations for why we see certain things in certain locations, not just continental drift. And at the same time, the mechanism that Wegener proposed to explain why the continents were drifting around was not accepted by most geologists in the Northern Hemisphere. Kind of people were really stuck in their ways at the time, and even now. Most people accept, I think pretty much everybody in the community accepts plate tectonics, but it took a long, long time. So Wegener's proposed mechanism, so his idea was that the continents plowed through the oceans. So here you can see here's a continent, here's oceanic crust. The continents plowed through the oceanic crust right here, and you can see in that process it's kind of bunching up the oceanic crust where it's moving in the direction that it's moving. And the continents were shifting around due to centrifugal forces from the Earth's rotation and gravitational forces that cause the tides from basically from the moon. But people realize that the forces from here or from Earth's rotation and from gravity from the moon are not enough to actually shift the continents through the oceanic crust. Those forces are not large enough. And so his mechanism to explain why the continents would be moving around was not valid. And so that shut down this idea for a really, really long time. And it took, so this was proposed in like 1915 or so, 1912, 1915. And it didn't really start to gain traction again until we collected more data in the 40s and the 50s. And in the 50s and 60s, that's when it really started to come together. So this was the early case for continental drift. But next we'll talk about some of the additional data sets that were gathered and some of the much more compelling evidence to suggest that the continents they are actually moving around.